more or less. Yes, thank you. So thank you very much, and thank you for the organizers for this very nice conference. Really glad to be here. So today I would like to talk about a computation which I did with Gyorgy, and this computation is about the propagator of the finite XXZ chain. And I would like to apologize in advance because it's going to be a bit difficult, and it's Friday afternoon, so well, I hope not all of you fall asleep. Well, I have a course. So, so to make it interesting and to make it more followable, so I'm gonna start, of course, with an introduction, but right away, like I'm gonna show the main result, which is it's a compression for the propagator, and after that, I'm gonna talk about how we completed this result. And the story goes like that: we found a method, how we could compute it, and then later on, our attention was drawn to another method, which is actually simpler. So I'm going to show both of these methods. The first one is based on the Trotter decomposition of the time evolution operator and some kind of partition function technique. And the second one is based on this twisted transfer matrix and spectral decomposition. And at the very end, I'm gonna show one equation which you can call, if you wish, an application, which is the Loschmidt amplitude for the domain-wall initial state. So exactly what Jean-Marie computed, but we have a much nastier expression, so it's rather a possible direction for further research. And then I will conclude, and yeah, and we can all go home. So we have this nice, very nice theories about dynamics, but what I'm aiming for here is rather a microscopic description of some kind of meta-body dynamics. So really, like if I would like to imagine this this project as part of some kind of larger research, and I would say that really the goal is to compute something from first principles, and then of course you have to start somewhere and then see how far you can go. And here we have our favorite Schrödinger equation, and we of course know what is the formal solution to this equation. And we would like to find the solution to this equation, I mean, for the XXZ spin chain. So, of course, all of you have seen this probably 100 times by now, but this is our Hamiltonian, where just for fix the so we're going to use periodic boundary condition, so we're going to be in finite volume, and then for some technical reason, which is not very important, our reference state is going to be the all spin down state, and then we're going to denote the elements of the spin basis as such. So A1, AN are the coordinates where we flipped a spin up. And then what we want to compute, we want to compute the matrix element of the time evolution operator between between two spin computational bases. Well, we want to compute this green function matrix element. And as I told you, I don't. I'm gonna right away tell the result, because it's actually pretty pretty suggestive. It's in a pretty suggestive form, and for that I just wrote down quickly the beta ansatz solution for the XXZ spin chain. So here we have the beta equation, where this capital P is the displacement, and this S are of course the scattering factors. And then, of course, if you have a beta ansatz solution, which are parameterized by some lambda beta roots, then the eigenenergy is given by the where this is your energy expression. Capital. Oh, it's L is the system size, so it's like e to the I. I mean, as you travel around the volume, that factor. Sorry, yeah. So L is gonna be your system size, and of course this is known. But I want to basically define these quantities, because if at the end of our computation, what we found is this beautiful expression, which we can analyze a bit. So this green function, where you evolve your particles, which are like spin-ups, from these coordinates a1 an to b1 bn, that's described by the following integral, where you have, first of all, you have, if you have m, sorry, here you have m is your number of particles. So if you have m particles, then you have m contour integral, and then I'm gonna tell you what is this contour in a moment. And here you have some kind of normalization factor. You have a wave function amplitude. I'm gonna also tell you, where you have a time evolution factor, so it's exactly e to the minus e t. I mean formally, but note that in the argument is of course actually the integration variable, and in the denominator you have the beta equations. So this is somehow I think a very suggestive form, and yeah. This normalization factor is defined here, and the wave function amplitude is maybe I draw something. So let's say you have 3 particles. They are evolved from this 3 position to these 3 positions. Then of course, so how this wave function amplitude is computed is that you take all possible I mean, you connect all these coordinates in all possible way. I mean, in all the permutations, and then, sorry, and then what you consider is for every particle you consider this displacement, which is as such for everyone, and of course, and also you multiply with this scattering factor in case these sort of trajectories. I mean, this is just I don't know, a pictorial way of thinking about it. If they scatter on each other. So I hope this is clear. And that's why I think it's a very suggestive form. But I would like to again emphasize that because everywhere you have the arguments are never on, so it's they are integration variables, and this contour goes around 2 point, which is this minus 8, like little contours around minus 8/2 and 8/2 in all u variables, and 8 is I wrote it somewhere, I don't know, is related to the delta anisotropy. So I think it's a nice formula, but of course the main drawback, I would say that the scaling of the number of integrals with the number of particles. So sorry, yeah, the C of eta is like a small radius, a small circle around this minus eta over 2 and 8 point and eta over 2 point. And then it's a technical thing, but these radii should be different. But what is kind of important that it's these radiuses, they are fixed. I mean, they are yeah. It doesn't depend on anything. You're always making your contour integral around these 2 points in every variable. So you can change a bit, but eventually you're gonna hit other singularities which you want to avoid. So you have to keep it sufficiently small. So I think it's sufficient if they are circles with some radius, and I think what is needed that they are sufficiently small, and they are all different from each other. So that's it. So yeah, it will be, yes, but actually, so this the pole, I mean, yeah. So the beta equations doesn't have pole around these points, like most of the cases. There is one case when it does, but okay, let's not consider that. But it's rather that this term, it has some ugly essential singularity around these points. So it's like, if you wish, you can think about it. I mean, the second method gonna be such that you're gonna that at first roll around the beta root, the beta root, and then yeah, and then you transform the contours to be around these 2 points. So if you wish, you can think about that. What you gain is that your contours are fixed, but what you lose that they are essential singularities. So it's this kind of game. More question? No? Are coordinates of upspin. So it's spatial coordinates, not beta roots. No, so it's a matrix element between 2 states of the computational basis. Yes. Because so, yeah. So okay, maybe it wasn't very. Maybe I could have been clearer. So your beta equation it looks like this. So this P describes the displacement of a particle. So why it's very suggestive, because you can think about it as you take all the possible permutations and then you just connect the initial and final coordinates and that much and with a straight line and that's how much the particles travel. I mean, this is just a pictorial description. It's non-physical, but yeah. Okay. So the 2 methods, these two, this Trotter decomposition of the time evolution operator, this twisted T-matrix method. So I would like to just give a short introduction in both methods. So the main idea here at this first method, and this was our original idea, is that okay, so you take the Trotter decomposition of your time evolution, and then this can be expressed as a product of the transfer matrix and the product of the transfer matrix and the transfer matrix with the switched auxiliary field. So if before you take the Trotter limit, so this capital N is still finite, then you can sort of imagine it that at the bottom you have your here you have your initial state. So this is the spatial coordinate. That's why it's a circle, because we use periodic boundary conditions. So here you have your initial state, and then you apply finite many, but a lot transfer matrices, and then on the other side you have to have your out state, and then with the number of circles you go to infinity, and then you want to compute. I mean, but what you want to do is you want to use the 6 vertex. I mean, you want to consider it as a 6 vertex partition function, and you want to compute that. So, yeah. And the other method is a bit different. So of course what you can do that. Okay, this not. Yeah. Okay, maybe this is okay. Anyway, so that you expand over a full system, and now I assume that this lambda is a full system, which is okay, not the best notation. And then if you compute these factors, then you are done. And then here really what is important, that you have to expand over a complete system, and that can be done in this for this twisted transfer matrix, which is a little modification of the normal transfer matrix, because for that case there are known theorems about the completeness of beta vectors. So do this in the twisted case, and then with the twist parameter you go to 1. I mean, you go back to your original untwisted case. So these are the two methods, and I'm gonna talk more about the first one, but okay, so I'm happy to answer questions. So this is rather introductory. So in order to do the Trotter decomposition, you have to introduce some tools. So here is our R matrix of the model. I can picture a depict like this. Here I define the matrix elements, and I again wrote down what's the relation between data and eta. And I don't think I should have mentioned that our computation works for any delta or any eta. So we don't restrict ourselves to any parameter. I mean, in this to any particular data. It satisfies a crossing relation, which I just wrote down because later on we're gonna use it. And of course, with them, with the R matrices, you can define a T matrix. Sorry, it's a monodromy matrix. So a capital T is the monodromy. You can define a monodromy matrix with this monodromy matrix element, and you can take the trace to have your periodic transfer matrix, and then graphically it's depicted like this. And in order to take the Trotter limit, you also have to define the auxiliary space reflected transfer matrix, which is you change the direction of the arrow. But what is important, what we're gonna use, that you can relate this auxiliary space reflected transfer matrix to the normal one. So there is some relation with some normalization and with some shift in the spectral parameter. And then, okay, I wrote down some ugly equations, but the point is that this operator can be decomposed as such, and of course you can expand t and t tilde around 0, and based on that, this equality can be proven, and then so you have something like t and t bar with some arguments, but t bar with the previous equation, you can rewrite it as t at some other value. So at the end, it's going to be a limit with some normalization factor of t's with the different parameters in as arguments. And here I have beta, which is basically related to the time. I mean this t. So how much time we evolve. So this is this Trotter limit, and for this case also at some point we need to perturb these betas a bit, but this is just a computational detail, not very important. And then I already saw this picture. You can, I like to think graphically, so you can imagine that here, this is your Trotter decomposition. This is the direction of the time. This is your initial state. This is or here, your initial state lives. Here, your final state lives, and you evolve with some kind of discretized time, where the number of lines, the number of horizontal lines is 2n, and then with this n you go to infinity, so make it like infinitely dense, and then you get your time evolution. And to compute this, we use this idea of the quantum transfer matrix or rotated channel. So we can look at this picture turning our head, and then we see this, and then if we look at it like this, then we can. So in the original model, these circles where the T matrix is, while here you have not exactly, you have something. I mean, you have these operators, and then you take a trace over them, and the number of operators is fixed, because as many sides I have, as many horizontal lines I have here, but the number of these quantum spaces, I don't know how to call them, they will go to infinity. And yes, yeah. So we have to know what are these, and then it's useful to think about again that I talked about this computational basis. So let's think about that. I have this here, and I have an initial state here, and I have a final state here. But I want to compute at the first approximation the matrix element such that here I put on the sides I put some spins, ups and downs as I wish. Okay, let's make it a minus. And also on the other side, I do the same. In some order, of course, I have to preserve particle number, but so I have something like this. So what I want to tell you by this, that at the end, okay, this is not here. These lines gonna be the matrix elements of the quantum monodromy matrix. So okay. Okay. So the quantum transfer matrix is formally defined more or less in the same way as the normal one. Well, it has 2n quantum spaces, and also the arguments are alternating because of this Trotter decomposition. But okay, if we are at finite Trotter number, it's all fine, and then we can still consider it as a 2x2 matrix with this A, B, C, D with the QTM superscript matrix elements. And then also here we can do some crossing, but it's again probably too technical for now, so let's not talk about it. And now we arrive at this picture. What I draw there, that okay, you can because of this boundary condition. This initial condition in this rotated channel, in the quantum transfer matrix channel, it's going to change into some kind of boundary condition on the two sides of the quantum transfer matrix. And now I can write down very ugly equations. But let's not bother about it. Okay, let's bother about it a bit. So if you are at finite n, this is really just a 6-vertex partition function, which well, we hope we can compute. That's the hope. And then if I include every normalization factor, and then I have to include this, and also here this basically. So this is like a specific matrix element of the quantum transfer matrix, and then which encodes my boundary / initial condition. Yeah, and then I have this the same information in a little more digestible form, because then I can. So I always confuse the direction of the arrows, but nevertheless I will try. So I think after some transformation, which I did, some switching the direction of all the arrows. If here I have my in state, here I have my out state. If there is a spin down coming in and there is a spin down going out, it's gonna be a D. And if I have a plus plus, it's gonna be an A. And then if I have an in is a spin down and the out is a spin up, then I have a C, and then a B corresponds to the last possibility. So basically the idea is that based on my initial and final state, so based on where I put initially and finally my particles, I'm going to have a unique trace over quantum transfer matrix monodromy matrix elements. So I think about this QTM superscript because I think from now on that's the only thing I'm going to use. So that's very nice, but ask if it's computable, and then you might think that no, it's not, because how this looks like, they are like, so for example, B is like somehow there is some spin down rotation at every site and summation over, and then but there is also these terms when I rotate 2 spins down somewhere and 1 up, and then also higher terms, and then it's all very messy and complicated. And okay, very nice. We have a useless equation unless I shouldn't walk to the other side of the room. Unless you come across this paper where they introduced this so-called F basis, which so it has some definition. Basically, the idea is that first of all you define these general R matrices which encode some kind of permutation. I mean, so if it encodes this permutation pi and apply it on a transfer matrices, then you're gonna get back the transfer matrix with the permuted quantum spaces. And then so these are like this I don't know, generalized R matrices, and the idea is that there is this invertible matrix F. It's F because it's factorizing matrix, which factorizes these generalized R matrices in the following form, and it follows from some kind of quantum group argument, which I don't understand. But what is very simple and what is only needed for now, that okay, it's a basis transformation. You can perform your basis transformation on your monodromy matrix, and then you can compute in this new basis your monodromy matrix element, and then you get these expressions, which are actually pretty nice. So this D in this F basis, it's just going to be diagonal. So you can also think about it as the eigenbasis of this D, and this B and C. They are. Let's look at the structure. So it's like I think it's diagonally dressed operators. So there is a spin flip operator at site I with some scalar factor, and it's diagonally dressed and summed over I. And the same kind of structure with C, just with sigma plus. And then okay, A has a bit more complicated structure. There is a diagonal part. There is a diagonally dressed part where the sigma plus and the sigma minus acts on the same space. And there is a third term where you have actually three parts. So you have a sigma minus on the side I, you have a sigma plus on side j, and this is diagonally dressed. But because we want this, we can perform this computation in this basis, and then it's pretty doable. So let's do it. So also some notation, I'm gonna leave out also tildes because who needs them? And also, if you remember at the very beginning, I said that the all spin down should be my reference state because I want to like rotate a few spins, and then typically I'm going to have a large number of d operators, which is diagonal. So that's why I chose the other vacuum. But I mean, this is also just a bit computational detail. And then let's look at one particle case. I have like 25 minutes. Or yeah, okay. So let's look at the one particle case. It's pretty simple, but this is of course, is the easiest case, but you can see how it works in this case. So what you are doing is you assume that your initial coordinate is 0, and you evolve the particle to site L, and then you want to compute this. And then, if your system size is capital L, it corresponds to this this trace, because so as I said here, so according to these rules, B like creates an operator on the inside, and C creates an operator on, or like annihilates an operator on the outside. So with these rules, if I didn't do a mistake, then what you should have that you create an operator, and then there are some empty sites, and then you make it disappear. If I maybe I confused B and C. Anyway, this is something you can compute. It's very easy to do by hand. I mean, it's 5 minutes, and if you do it, so I introduced some kind of notation for this. These are like basically functions. So yeah, so these are basically just functions of the R matrices. Just I use some shorthand notation. And also I keep myself general, so if you remember, in the Trotter limit, there is some kind of different rapidities here, but now I'm just going to keep myself general and call them xi. And under this notation, this trace is just easily computed. And then, okay, now you have to take the Trotter limit, because now you have, if you wish, the 6-vertex partition function, but you have to take the limit in order to compute the propagator. So you substitute. I mean, you substitute back your beta with this prescription, and then you right away realize that some singular terms, and in order to get rid of the singularity, you try to write your expression as a contour integral, and if you want to make, so you want to make this right side to be equal your finite partition sum, and you can just based on this identification, you can figure out what is your f and gj functions, and if you do so, these are the functions you get. And basically, you can see that here, like this, for example, the one particle beta equation here shows up, and I mean, this start to make sense. And after rewriting it as a contour integral, you can perform the Trotter limit, and then you end up with this expression, which, if you rewrite it's exactly the one particle case of the general expression. So this is just the one particle energy. This is the oh, sorry, no, I should talk about, yeah, sorry. So this is the one particle energy here. This is the beta equation for one particle. This is the exactly this displacement corresponding to the displacement of the particle, and this is some normalization. So this is how it's reconstructed. Now the drawback of this method that for every different kind of configuration you have to repeat your computation, and then after a while you realize some kind of patterns, and then you try to prove it generally, and then it gets messy. But either way, the same way you can prove it to the case when the particle doesn't move, then you have to consider a different kind of trace. The similar computation, basically you end up to a very similar expression where this factor is missing because the particle stays at the same location. T is in beta, so yeah, I was a bit, it's in beta, so beta is something like sin eta times t or something like that. Yeah, I didn't rewrite it in a form as I presented it in the first equation, but I hope at some point it's going to happen. Okay, yeah, okay. I just rewrote it like this. So this is if you take all those factors, then you recognize this form, and then you reconstruct this for one particle, and then of course it's actually so here for one particle you have one contour integral. So it's very simple, but maybe it's worth to look at the pole structure a bit, because we can still draw it in 2D. So you have so the contours going around these 2 points, -8/2 and 8/2. So they are little contours. They should have different radius, but well, here they don't. And you know that at least for these values of delta, your expression, your integrand, has poles when the beta equation is satisfied, because then this term is 0. So, and then for this value, you know that they are symmetrically placed along this imaginary line. And then it's kind of suggestive that, okay, and those are all the poles you have. It's kind of suggestive that, okay, you can blow up these two little contours all the way into this these two dashed contours, and then you can like shrink it back on each and every beta state, and then what you get back is spectral sum. And okay, this is very simple for one particle, but with the second method, this is basically what's done just for in a multidimensional case. And okay, just to share some of my sufferings, but not too much, just a little. I would like to just show how what kind of computations I had to do, because okay, you compute one particle, it's very simple, but you have to do other stuff too. So you go for two particle, and then the first thing what you realize that okay, because what you write down in the trace depends on the spatial distribution of or in and out particles. That's why you have cases to consider, and up to periodicity there are these 5 cases where I have to consider different kind of traces. And here again I introduce some kind of simplification, because so this D that's like the empty states. It's you can put in some I mean, it's easy to compute this quantity with any kind of operator, because D is diagonal. So it's so I just So you can imagine that between creating and annihilating these particles, there are just many Ds according to these exponents, but yeah. And then you go through all of this computation. It's a bit more complicated, but you can do it. So again, this is one case I wrote down. You get some nice expression, and then it's again singular, and you again want to rewrite it as a contour integral. So you use the same method as previously, just now with double integral, and then you take this generic form, you expand it over summing over the poles, and then you want to identify this summation over the poles with different terms, and then for two particle cases, it's still doable. And if you do so, after that taking the Trotter limit is not so difficult, then you end up with this expression, which is exactly this two particle case of the general expression. So you have the two particle beta equations in the denominator. You have the time evolution with the two particle energy. You have two normalization factor, and you have this two particle wave function amplitude. This two particle wave function amplitude depends on your in your cases the different position of the particles. And if you draw these, and these amplitude, okay, I didn't list all the 5, but just 3. These amplitudes can be identified as follows. So you have to again sum over all the permutation, which is in this case just 2, and then you connect your incoming and your outgoing particles with straight lines. And actually, in this formalism, there is this kind of apparent always forward propagating, but this is non-physical. It's a computational detail. This we can get rid of, but okay, I won't talk about that anymore. But if you make these little drawings, then it's very simple, very suggestive to again figure out what are these factors. Nice. And then maybe you want to do it for case. So maybe you want to do it for generic case, but then I sort of did it, but that's very nasty, because then that's complicated. And then rather I switched to another method, which I'm gonna actually talk about it much less. So here I'm just gonna basically show the basic idea, because what do we want to do? We can just do a spectral sum. We can just if you wish, we can just do this expansion over some full system, but we have to know that this is a full system, and this is where this paper of Kitanin, Maye, Slavnod, and Terra is very useful, because in this paper they talk about a so-called twisted T matrix. So you can introduce this diagonal twisting matrix M, so it's a diagonal matrix with matrix elements kappa, where kappa is a non-zero complex number, and then you build up your twisted matrix as that between every R matrix you twist auxiliary space with this operator, my matrix. And then there is some kind of twisted beta ansatz for this case, like with the usual ingredients. They are just they have this kappa as a parameter, and then this is a way to write the twisted beta equations, but this is basically, I mean, you can recognize the normal beta equations as after just some algebraic change. And the idea is that in this paper, for twisted models, they proved a certain solution, so-called these admissible off-diagonal solutions, that they form a complete system. And then you can first, if you consider the whole propagator in the twisted case, and you want to compute this operator, twisted propagator, then you can do this, and you can use this completeness to use the spectral decomposition. And after that, if you take the kappa goes to one limit, then you can actually right away derive the generic result. So I won't talk about this anymore because probably it's already too much details. But if somebody has interested in more details, I'm happy to discuss. So this is basically what I wanted to tell you. That okay, we have this nice expression. Well, you can ask if it's nice or not, but what can we do about it? And then, well, let's compute something fairly simple. And then one way of we can yes. So we can, for example, compute Loschmidt amplitude and some kind of a smart choice of initial state is this domain wall state, and this has been computed by Jean-Marie. So if we could compute this, it's just a reproduction. But anyway, what we do here, that if you want to compute the overlap of a beta state with the domain wall state, then you can actually write it down as an Isers-Ginkorán predeterminant times frozen part. Then by using this substitution, you can give an exact expression for the domain wall Loschmidt echo in finite volume. And I don't know how useful is this. I mean, if I want to compute some thermodynamic limit, then with the number of integrals I have to go to infinity. So this is we will see what we can do about this. But anyway, I hope that at some point it's going to be useful. And this is not. And then with this, I would like to conclude. So what we computed is contour integral formula for spin-1/2 XXZ chain with periodic boundary conditions. So it's finite volume, and then it's on fixed contours, and we have there are basically two approaches what we used, and prove this formula, and then let's see how much you can apply this to our original idea to compute some kind of quench dynamics from microscopic physics. And we have this, I mean, here you can find the details. Thank you.
Yeah, so okay, look.